Okay, so we should be starting soon. Is Candace back? Maybe the panelists can turn on your cameras. Okay. So, hello everybody. Thank you so much for joining us for the 5th episode of our panel discussion series, Careers at the Cutting Edge of Technologies. Today's discussion is on careers in VLSI and embedded systems. I'm Sudha Kumar. I'm the director of the USC Viterbi India office, and I am based in Bangalore. We are all right. So sorry about that. I had my video off, but I am now on. I'm Sudha Kumar. I'm the director of the USC Viterbi India office. And so what we're planning to do today is while you were registering, we had asked for you to put in your questions to the panelists. Many of you have done that. What we'll try to do is fold in many of those questions into the discussion today. You can feel free to send us more questions on the chat site. And if we do have time towards the end, we will take those questions as well. So let me go ahead and start introducing our really wonderful panelists. We are very excited to have Dr. Sandeep Gupta, who received his BTech from IIT Kharagpur in electrical engineering, and his MS and PhD degrees in electrical and computer engineering from the University of Massachusetts, Amherst. He is the professor at Ming Sheh Department of Electrical and Computer Engineering at the University of Southern California. At USC, he has served in various roles, including that of the president of the Academic Senate and the chair of the Electrical and Computer Engineering Department Systems. His current research interests include design, test, validation of digital hardware, especially emerging technologies and software. Welcome, Sandeep, and we are really looking forward to hearing from you. Our second panelist is Vivraj Karadya, who is one of our alums, and we are delighted that he's here today. He has over 12 years of experience in the high-tech semiconductor industry. He is currently physical design lead in the ARM server processor group at Marvell Semiconductor in Santa Clara, California. In the past, Vivraj has worked in various domains of VLSI like verification, post-silicon test engineering and validation, circuit design, physical design at companies in India and in the United States. He's constantly striving to connect academia and industry and has delivered several lectures in topics relating to VLSI and the semiconductor industry. Our third wonderful panelist is Candace House-Texera. She is the Associate Dean, Corporate Engagement and Programs at USC Viterbi. Among the various other hats that she wears, she oversees the Engineering Career Center. She has served on the USC Viterbi Industry Advisory Board, the Corporate Council, and was a lecturer for the Information Technology program at USC. She's currently pursuing her doctorate in policy planning and development at USC. Welcome, Candace. So today, Sandeep will just start with the basics because many of the students are freshers. We'll start slow. What is VLSI and embedded systems, and why are they important to industry?
So I don't know if my audio is working.
Yeah, it's fine.
Okay. So, think about almost everything that we do today is information being processed digitally. And you can think about a digital system in a variety of ways. One way is that you go by chips already made by other companies. You can buy a microprocessor from Intel. You can buy a video processor, graphics processor from NVIDIA, and so on. You can go buy wonderful platforms that Marvell and other companies make. And so you buy these chips from these companies. You don't design the chips. You basically buy them, and you build a system around that. You say, well, this chip can do this, and if I write the software, and if I connect this chip to this other chip, and I write all the software just right, then I can build a system that does whatever I want it to do. So that would be an embedded systems approach, where you are actually assembling together a system, either a pre-made board that you buy from somebody, or you buy a number of chips and you design the board and you design the software. It could be both, and the board can also have connection to sensors and actuators, so it can basically collect data from various. It can make temperature measurements, it can make measurements of various gases, concentrations, and so on. So you can design this kind of a system, and that would be called a generally embedded system. Now, so there what you're doing is you're designing not at the level of, you're not making the cloth from scratch, but you're buying a shirt and a pant and, pair of pants, and basically you're building an ensemble. And you're building the ensemble to basically sort of do something particular. You're doing it, you're building a costume, but you're not starting from making the thread. So that's sort of a view of embedded systems. Now, in general, there are embedded systems. You can think about anything that requires digital processing, which is now everything. So embedded system can be just a hearing aid that goes inside your ear cavity. It has fairly sophisticated things, not only a microphone that picks up the sound, but a very sophisticated system that cleans up the sound, reduces the noise. It changes it is tuned to your hearing deficiency, so it will accentuate the frequencies that you are deficient in hearing, and so on. And so it's a very sophisticated digital signal processing system, and it's all, including the battery and everything, is basically inside your ear cavity. So embedded systems can be very small. A pacemaker is an embedded system. But on the other hand, at a meeting a few years ago, I was basically talking to somebody from Navy, US Navy, and he said, for us, an aircraft carrier is an embedded system, because essentially an aircraft system has basically huge amount of digital processing, all sensors, actuators, radars, sonars, everything basically working, and controls, because we have to coordinate the approach of the aircraft and basically the slings that operate them and that control their basically landing and capture them during landing and eject them during takeoffs and so on. So they think that so embedded systems can be small, they can be large, but the idea is that they are usually designed to serve a specific purpose. They are usually designed by assembling things that you don't design from scratch. So you're not making the cloth, you're buying pants and shirts and building an ensemble with that. So, and they usually require a lot of hardware and software design. So that's sort of my take on the embedded system. VLSI system, let me basically, just say, so now in VLSI system, you're actually designing those chips. So maybe I can, Vivraj, since he does it day in day, I've been teaching VLSI design for 30 years, but I'll let Vivraj, one of our illustrious students, to basically sort of take that portion of the question.
Sure, thanks, Professor Gupta. Yeah, so VLSI is basically, as Professor said, right, it's what builds the embedded system, right? It's basically the raw material for the embedded system, let me put it that way, right? These are the chips that basically, are designed to perform a specific task on an embedded system, right? Let me take the same example of an hearing aid, right? So there could be several chips on that hearing aid, right? There could be a chip to just basically capture the analog audio and convert it to a digital, signal that can be processed, right? And then there is a small specific, application specific processor on that basically enhances it, digital signal processor that enhances those signals, that will filter out all the noise and then basically modulate and do all of that, right? And then there will be a chip again to convert back to an analog, so that the person using that, it basically amplifies or does whatever it needs to, right? So that the sound is basically going. So all these individual components that are there, right? These are basically standalone integrated circuits or ICs, right? Nowadays, these are a little more complex, so we call them system on chip. So there could be multiple of these on a small, but they're all packaged together within one package that you see. So that's a system on chip. But these essentially are nothing but VLSI chips, right? What we call it, some call it integrated circuits. That defines VLSI to me, right? So and essentially, it's everywhere, right? Semiconductors or VLSI or embedded systems is everywhere around us, right? Our lives are pretty much revolving around that right now, I could say, right? From medical devices like pacemakers and hearing aids to all the massive cloud computing infrastructure that's out there. So yeah, so to me, that's my take on VLSI.
Wonderful. Now that kind of covers everything briefly. Uh, so Sandeep, what are the recent advances in chip design in the world today?
So, the chip design has been around for a long time. I think the integrated circuits became possible in the 60s, early 60s, late 50s, early 60s, different types of integration started. And we've gone through this amazing 50-year journey. I give a challenge to my students. I teach a seminar course sometimes in spring when I have time. And I ask these graduate students, I give them examples of all walks of life, from dams and bridges to aircrafts and automobiles to antibiotics and vaccines. And I give them this simple challenge to gene sequencing, all of that stuff. And I give them a very simple challenge. I say, find me one other thing in the world which has grown at a high rate exponential for 50 years continuously. And nobody can find anything. The longest period they can find a lot of things that grow 3-4% a year. That's normal life, And and by the way, I'm talking about something where a technical parameter is improving. The number of cell phones in the world increasing is not the thing. How much better the cell phone is becoming is the criteria, is a valid thing to study in this. And they find basically, two examples jump out. One is flight. When they started flying airplanes, the length of the flight and the height of the flight, altitude of the flight grew exponentially for 20 years, then stopped. And so this is an exceptional thing in semiconductor, that the semiconductors have grown at this exponential rate. As a result, what has happened is that's why basically everything that was used to process, we used to have mechanical computers, we don't have them anymore. We used to have, a lot of things that would be done in certain way with using, other things, but now we process it as soon as possible, we convert it digital. As Vivraj just said, you start with anything, you convert it to digital, you do a lot of processing, and then you convert it back. And we do that. So we don't send messengers anymore. We send signals. Basically, we scan things and email them. And then we convert them and print them if you want to print them. So in that sense, this technology is becoming faster and faster. Now, what has happened is that as a result of that, the devices are becoming smaller and smaller, and you can put more and more of them on a single chip. And that basically means that you can, at a lower cost, at a lower power, you can get more computing done in a small chip, and you can basically, build these more and more complex systems. So the first challenge in the industry for the first 20 years of this exponential race was, how do we design? In the beginning, it was fine. You're designing a chip with 10 devices, 20 devices. There were chips in the 70s, late 70s. A chip with about 200, 300 transistors was a big chip. And so you could, design complexity was not an issue. But in the 80s, design complexity was reaching basically the level of, hundreds of thousands, millions, etc. And in the 90s, it basically reached 1 billion. So at that point, you are basically not designing 3 houses in a plot. You're designing entire country, states, housing for the entire state, and that required huge amount of coordination. So the challenges early was how to scale up the design process and how to basically rationally divide it up so that different teams of engineers could work in different things, yet when they put it together, everything works. So managing large projects, doing creatively, designing taking a big function, the big thing that you want to build and dividing it up into smaller pieces, and then having different teams work on them, coordinating once in a while, but getting everything together, making sure once everything is put together working properly. These were all concerns, but scaling up was the main concern until basically 90s. Now in 90s, the exponential growth continued, but instead of basically the size of the transistors becoming smaller at exponential rate, power becoming lesser at and speed becoming higher at speed becoming higher at an exponential rate, cost decreasing at an exponential rate, and delay also power also decreasing at an exponential rate. Suddenly the power didn't decrease anymore. So now suddenly you have to do these large projects, even larger projects, and you have to worry about managing power because there's not enough power you can bring into a chip. Some of these chips were 150, 200 watts. Like, imagine that's like a quarter of basically a hot plate. And the density, these chips are very small, so the density of energy was very high. So then essentially, in addition to keep scaling up this thing, the challenge became how to basically make sure that it doesn't consume too much power. Now we are at a point where we can put more chips, more transistors on a chip, big chip, or system on chip, as Vivraj mentioned. But we can't power them all. If you power them all at the same time, the whole thing will fry. So there's this notion of dark silicon. So we have basically, in the sense that we are building colonies where every house cannot be occupied at the same time, only some of the houses can be used. And we still think it's beneficial sometimes to basically do that. So power became a concern. Then what started happening is that even though the transistors became smaller and became faster, they started becoming unreliable. So then people like me had basically opportunities to basically say, hey, we have to check this design very thoroughly. This thing, previously we used to think that if you design it this way, it will work, guaranteed to work. But now even if you design it carefully, it is not guaranteed to work. So we have to actually take our design and fabricate them and actually debug it and test it and make sure, validate it, that the actual silicon actually works. Just because our models say it works, our simulators say it works, it doesn't necessarily work. So validation, verification started to become a bigger part of it because this thing started to become imperfect. So you are able to build. So you may be able to build, and basically previously if you may have built a chip, a big chip, and you may have sold 90% of the chips you fabricate and throw away 10%. Suddenly you were throwing away in the early day, in late 90s, early 2000s, there were instances where you were able to sell only 3% of the chips that you fabricate. And you can't work at those economics. So you have to basically sort of put in a lot more effort, make your designs, you have to work, do the design, check everything in simulation, but then fabricate, and you have to test and validate everything. And when things didn't work, you have to go back and debug, find what was wrong, go back, change the design, repeat the process to basically get 30, 40, 50% of the chips that are sellable. So 30, 40, 50% of chips that actually you can sell are amazing. They're much better than the chips from previous years. But getting back to 30, 40% from 3 or 4% when the first day you put a design and start fabricating it was a lot of challenge. And that has changed the complexion of a lot of these companies and a lot of the jobs in the area where so now you're not only a designer. So you think about a designer as somebody who basically, is a visionary who basically says, this is how you do things to make it better. But now you have detectives saying, no, I want to investigate. I want to make sure this really works. I want to challenge this as much as possible. So you basically have a very different way of thinking. A designer is a creative person who basically develops ideas and develops good practices to get things to working. Yeah. But a test and validation person is actually takes an antagonistic role. He says, it is my responsibility to make sure that if I sign off on this, then my company will not be embarrassed by a lot of chips that actually don't work. We don't give customers chips that don't work. So their job is actually to be hardcore investigators, to really challenge the design. And when things don't work, then do investigation why it is not working and provide feedback to the designer saying, hey, you have to do this differently because we found the problem is in this tiny part. Okay. So that has basically grown. And now the next development is basically other technologies are beginning to, as CMOS basically slows down, actually these opportunities keep growing. So the way I look at it is that, if you had if you have an underlying technology that is improving at an exponential rate, if everything was improving at an exponential rate, VLSI designers would basically be just, doing the same thing, just bigger and bigger. But in reality, it has been growing better and better, but new challenges have emerged. That gives a lot of lot of intellectual, professional opportunities to people who are in the VLSI space, because every challenge is something that you have to conquer, and that requires people to basically be trained at a higher level, requires them to work at a higher level, it requires them to have, there are more jobs available from a very practical point of view. It's very difficult to basically find people with that level of competence and so on. So that has basically been a great opportunity, growth opportunity. And I think there are other movements that I'll talk about later of basically this technology slowing down that actually creates opportunities in two different ways, in design and in new technologies. So I'll talk about that. I think there are other questions later that I'll come to that.
Right. Okay, so actually the next question, I'm just blown away by your 30% or 40% that will work, because that just seems so much wastage. But yeah, so the next question is actually is actually an audience question, and that is, how has artificial intelligence and machine learning technology impacted the VLSI embedded systems field?
So from my perspective, I mean, there are two ways to think about it. The machine learning is a tool, and that is used basically, one way to think about it is that it is used in the design process a lot. So just give you a very simple concrete example that has been around for 20 years or 30 years. One of the things that happens is that you basically have to use the way the designs that we make for circuits are actually set of polygons, mostly rectangles. So your design basically looks like just a bunch of rectangles of different colors, okay? And all the blue rectangles are one thing, all the pink rectangles are another thing, all the orange rectangles are another thing. I'm just making up the colors because the colors sort of have changed over the decades, okay? And so then those rectangles are one set of rectangles becomes one negative, if you think about it as a film negative. It's a very high resolution because these rectangles have resolutions of now microns, right? Nanometers. So they're tens of nanometers. They make features that are basically, making the feature off by 1 or 2 nanometers may make a big difference and may make the difference between working chip and not. So it's a very high resolution. And when you make these pictures, when you take pictures of this, you need a light. So you have a negative, you shine a light, and then it falls on the chip, and the chip has some chemicals on it. That's, it's now a piece of silicon, and on that you have smeared some chemicals, and that would react with it, and there would be a different reaction where the light falls and where the light doesn't fall. And that's how you actually build these things into layer by layer. And it's a painstaking process, and it's a very error-prone process because it's a very high-resolution process. Now, one of the things that has happened in this process is that the light that we use is really not suitable it's suitable for something to make in 200 nanometers. But, so we should not be making rectangles with resolution less than 200 nanometers with this light. But we are stuck with this light because the next light that is available for us that can be used in this process is very expensive. So we stick with that. So now suddenly you are using basically, so imagine this, that you are making a fine jewelry, but the tools that are available to you are the tools that you get from the hardware store.
Yeah.
So you have a hammer, you have a plier, and the plier only works for basically used to handling screws that are like 3 millimeters wide and so on and so forth. And you are suddenly now working with things that are a fraction of a millimeter, and you are using this tool. So a lot of machine learning has been done to basically say, no, this light is we can figure out how the light is going to basically distort these images. So if you want rectangles to eventually look like this, then the rectangles should be that you draw the rectangles the way you want them to be, but then you change the rectangles to be something different. It's called, optical correction, OPC. And so you say, if you want rectangles to look like that when it is manufactured, we know light is going to distort. So we are actually going to distort your rectangles in such a way that when the light distorts it again, it gives you what you want. So it's a very complicated game that we've been playing for 20 years now. And it's been possible to use this cost-effective technology to build these smaller and smaller devices. And so this is just one very prominent example of this kind of a machine learning methods that are used. The second is basically where VLSI industry can feed and build chips that can accelerate machine learning. So it's like, sometimes, VLSI is held by machine learning methods which run on servers. but then VLSI can produce chips that can make machine learning faster. So it's sort of the VLSI field is both a consumer and producer of machine learning and AI from that point of view. So we can talk more about that later.
Okay. Vivraj, you want to weigh in on this?
Yeah, sure. Actually, I'm more of the producer side, right? So maybe I can add a few more comments on that. Professor touched in elaborate on the consumer side of things and technology. So producer side, right? I mean, pretty much everything around us that's happening these days, right? Think of it from autonomous vehicles, driverless cars to intelligent computing that is happening, right? All of this is driven by the requirements of machine learning and artificial intelligence, right? At the crust, right? Basically, there is an application requirement, which is a machine learning, thing. Think of it as basically these, cloud computing that's happening, right? Now that demanded that we have hardware that supports that, right? It's not going to be just any normal, processor or, based on, old one human architecture, for example, right? That's going to work. It has to be, completely redesigned, rebuilt, right? So then came the requirement to basically come about and innovate in the industry as to build application-specific or AI application-specific processors, right? And there are numerous companies and numerous technology advancements happening, and probably we'll touch that about the companies a little bit. But I think just my take on that is the overall requirement, and this is exponentially growing. To me, now any application you take around you, right, is AI driven, right? There is some sort of artificial intelligence inbuilt into it, right? It could be your smartwatch, right? Think of it, right? So I feel that, there are a lot of opportunities, and this is fueling the VLSI industry going forward.
Okay, wonderful. So one more audience question. Vivraj, let me have you answer this question. Is there still scope for development in VLSI? This is the question from one of the audience members. I hear people talking about how the semiconductor technology has come to a standstill and Moore's law has started to fail.
Okay, so true. So let me step back a little bit, right? So basically, from the technology perspective, yes, it's getting more and more challenging to reduce the size, make the chips more and more smaller, as Professor was just telling a little bit ago, right? It's as we go from 16 nanometer to 7 nanometer to 5 nanometer, it's becoming really challenging, right? And probably what's beyond 5 nanometer, it's all in research, right? So yes, as a Moore's law is now becoming, as a technology in that sense is coming to hitting a little bit of a wall. I won't say it's a complete stop. I'm pretty sure the way we thought it's an end at 45 nanometers, and then we got to 28, and then we got to 16, and then we got to 75, right? So we'll go beyond that, right? I don't have any doubts about that. But basically, the amount of applications, right? The amount of the amount of applications and the requirements of the industry in terms of coming up with different kind of products has increasing exponentially, right? So while the technology, people still use the same technology for a longer span. Initially what used to happen was a 45 nanometer lifespan would be like a couple of years, and then the whole industry would move to like 28 nanometer, and the whole industry would move to 16, right? Now the industry stays on a technology node for much longer, right? It probably stays for 5, 7, maybe more years on 7 and 5 nanometer as we are today, right? But the amount of products that are coming out, right? The innovations that are happening, the requirements, right? Think of it, right? We didn't have autonomous vehicles before. Think of it, we didn't have smartwatches before, right? Look at the advancements happening in the medical field, right? There is still actually a lot more to even come up in the medical field. So I feel it's I don't see any shortage of innovation or work in this field. While the technology is slowing down, this industry is still moving ahead with full steam, and we have lots of opportunities in that domain.
Okay, so the next question is actually just to take off from that particular question is, what do you see as the future in this field? Is there going to be growth for people opting for a career in this area.
Absolutely right. Again, it's kind of tagged along the same previous comment, right? I mean, okay, so before, right, we, people used to come and work more on the technology and think, okay, how do I take this further, right? Now, I think the requirement in the industry, and it doesn't change the fundamentals, right? I still feel that we need to know our circuits and transistors and stuff very well, right? It just shifts the vision of the people as now moved a little bit beyond more than just the technology itself, right? It's gone beyond it's gone to the applications, right? Let me take some examples of, um, think of it, right? Today, we've been building so many complex systems, right? Now has come an emerging need to basically think of solutions in the security domain, right? We are having so much of cloud computing. We are having so much of devices that are connected, right? That calls for advancements and coming up with products which are security chips that basically make sure that all of our data is secure, all of our transmissions that transmit data here and there is secure, right? So those kind of those requirements are still there and they're growing, right? So I would say definitely there is tremendous scope in the field out there, right? It's just gone beyond the technology, right? I'm sure basically the technology will also advance, and there are a lot of research areas that are being touched on, and probably we'll come to the research domain a little bit later. But yeah, I guess simply put, right, semiconductors are everywhere around us. So it's integral part of our societal needs, economic growth, and overall security, right? So you need to come up with designs that support all.
So this is not going to go away anytime soon.
No way, right? Because
All right.
I mean, essentially, think of it, right? Could you be able to now think? Could you think living without a cell phone? Could you think living without a smartwatch? Could you think living without cars that are more smarter, right? Simple things, right? Sensors in your tires of your car. They make your life, and we will try to innovate those kind of products, right? So I'm sure that, and this is all within the bubble of semiconductor industry, right? So
Yeah,
that's my take.
very good. Candice, what about you? What are you seeing interest in companies coming to hire in this area at USC? I know that later on you'll be showing us the slides which have the names of the companies that hire our students. But at this point, I was just curious about the general sentiment.
Absolutely. So companies are continuing to come to campus and now virtually recruit our students in the field. The list of companies is quite long, but just some of the regular recruiters. Marvel is present at USC in the School of Engineering, but also Apple has done a good amount of hiring, as well as Intel, Texas Instruments. The list goes on, and we'll be able to go over that. But there has not been a shift in the interest for students with this discipline, either for internship or full-time opportunities.
Wonderful. Good to hear that.
Can I add a point? Can I add
yes, go ahead.
So, right, just let me give a perspective of growth-wise. I'll give some numbers, right? So Marvell just last summer, right? Even with this and the internship program just ended. It's ending this week, right? We had 82 interns virtually from across 30 universities, right? And these are all virtual interns, and a lot of them actually are in process of getting offers who will join next year, right? Because they're returning back to school. So and again, right, this number has been growing, right? And I think we'll somewhere touch the fact of a difference between a fabless company and a fab company, right? Maybe we'll come to that, but that basically can also answer the question that, don't think of it as a semiconductor company which has its own fab and makes chips, right? Most of the semiconductor companies are fabless. But I'll defer that to maybe later if you have a question.
Yeah, that's wonderful.
So let me kind of give
okay.
a high level perspective, just 1 minute, okay?
Sure.
Think about it this way: the fabrication facilities are like, actually are very expensive. They have very expensive equipment. They are basically results of a lot of experimentation before that, but they don't employ too many people. That's the reality of it. because anything that processes is automated, because something that processes at that level of precision, most people are essentially there not even to calibrate the machines. They are there just to basically, when machines fall apart, so to speak, just do maintenance type of thing once they figured out. So there's a lot of people involved in the labs that build these devices and everything, but once it is built, it operates with not too many employees. So that's one thing. The opportunities are much larger, much more voluminous in the design space, design verification, validation space. And second way to look at it in a very macroscopic level is that so the reduction in the number of fabs or whatever is not really a harbinger of lower jobs, is what I'm saying. That doesn't make an effect. And technology, everything improves exponentially, then everybody's a genius. Okay, and you don't need too much talent, and you don't need too many people to do the design. Okay, but when things become harder, which is what happens when basically things flatten out, you really, so I'm just giving you a very high macroscopic sort of a macro level argument. That is when you need not only basically more dedicated engineers, highly trained engineers, specialists in their areas, and basically doing a lot of work to make things work. So when things are easy, actually the number of jobs is smaller. When things are hard, the number of jobs is higher, and the job is of higher quality, greater degree of satisfaction. So you're not a detective who's basically talking about lost cat. You are a detective who's actually you. If you're a detective, you want crime in your city. I mean, so you want technology to basically be challenging if you are a detective. So that's from that sense. But the third thing is that making this application-specific chips that Vivraj was talking about, that you're designing chips now specifically for a watch. You're not using the same chip in the watch as in the laptop because they have very different set of functionalities. That requires a type of creativity that hasn't existed in the field for a long time, because essentially what happened is that there were 5 or 6 broad categories of chips that you designed which were large and challenging, like a general purpose processor, that, graphics processor, a DSP processor, and there were 4, 5, 6 big chips, memory chips, DRAM chips, SRAM chips, and you designed this sort of 4 or 5 big chips, and then everything was basically done by composing them. But now you have to basically design something that is specific, and for those 4 or 5 things, there were textbooks written. Hundreds of textbooks will tell you how to do it. Thousands of professors will teach you how to do it. A lot of experienced engineers know exactly how to do it. But now there's an element of creativity, because there's a new frontier. And how do I do this? I have a different type of material. I have a different type of challenge. I have a problem that is not the general problem of basically running this type of code faster and faster, but I have a problem of doing a different type of processing. So I have to think differently. So there's also there's a more technical challenge and room for basically more technically oriented people, but there's also room for more creative people who can actually think in fundamentally new ways of new problems, not like a new version of an old problem. And so just modify the approach for the old problem, but to actually think. And this is the direction that some of my research is taking right now. We are designing digital circuits. And for the first time, we are designing digital circuits that our colleagues say, surely that won't work. And that has not been, in digital circuit, that has never been the thing that you hear from your colleagues when you design something. And when my student talks about some of this stuff, they say, surely that would have all these challenges. I say, no, we'll fab it and we'll show you that it works. And we have basically, so there's a lot of element of creativity here. So that's sort of another thing that I want you to understand is sort of, it's like more opportunities. Diversity actually leads to opportunities because the market is not going away. See, if market was going away, then this argument will not hold. But the market is not going away. And because of that, you basically have this extra opportunity.
Okay. Well, that actually sounds very exciting for someone who wants to get into the field, because I think if it's creative, then that makes it very nice for them. So, Vivraj, you've been in this industry for 12 to 15 years, and I see that you have had a variety of experiences in this particular area. So my question to you is, what excites you personally in your career? What is it that gets you up in the morning and ready to go?
Every day morning is my boss. I'm just kidding. Okay, so it's passion, right? I'm always passionate about working in a domain that allows me to innovate, and I'm not just making this up, right? I mean, I think of myself working in some domain, right? If it were not VLSI, what would it be, right? Where essentially there is, not much innovation, right? I can't be a machine who would just churn things out every day, right? And I think passion to innovate and interest in electronics, right? And this crosses, basically, when this crosses, this basically is the semiconductor industry, right? Now, another thing is basically it gives me an opportunity to work on products or things that the world will see tomorrow, right? Um, like I'm working, I mean, always, right? Any engineer working on a product is basically going to come to market in maybe 1-2 years, right? So that basically kind of you know keeps me moving, keeps me going ahead, right? And then again, there is just so much more, right? There is just so much more work out there. Like I've been in this industry for almost 13 years now, and every year, right? It's almost like going back to the basics, learning, the new technology. As soon as the new technology comes, right, you go back to scratch. What's the resistance? What's the capacitance? I mean, you just do everything again, right? So that kind of gives me a platform to always even learn, right? So those are the few things that I think of working. And then again, at the end of the day, it's a cutting edge products, right? And again, I'll take an example over here, right? Few years ago, we were all just looking at a processor from one angle, right? We all knew the processor was okay. It was Intel, and it's the processor that sits in a desktop, right? Now, can I use that same processor for a computing machine that is basically now processing your data as, let's assume, for example, Facebook or Twitter or all those things, right? No, we cannot, right? We cannot put 10 of those processor chips and you cannot think that it'll all work together. That came the requirement where, okay, now we have to rethink a processor design that is specifically for this, so that's when started the revolution of server application specific processors. These are big processors, power hungry processors, but they process lots of data, right? So some of these challenges makes me going, and I guess the one last and the most important thing that keeps me going is, hey, there is good money in this industry.
Well, that's important, of course.
At the end of the day, yeah, I think let me jokes aside, right? Let me just say that the amount of opportunities is just tremendous. And another thing, right? Let me add to that is now it's not just becoming an hardware specific industry, right? There are opportunities where you could actually have multiple things. You could learn multiple things. You go to an AI company, right? And you're working on an architecture of semiconductor design, you would also have to have some background of software or compilers, right? So that gives me a platform to kind of cross learn. That's what's keeping me going.
So it's actually been really nice to know what exactly this field is about. But now we come to the next part of our panel discussion, where I think many of the people in the audience who are maybe undergraduate students currently, or just working professionals with 1 or 2 years experience. And what they would like to know is, when you hire somebody, what kind of skill sets are you expecting? And how should they prepare to do well in this area in their careers?
Sure. So, okay. So there are two aspects to this, right? If a company is hiring fresh graduates, or if I'm looking to hire a fresh graduate, right? All I'm looking for is strong fundamentals, right? I think basically just make sure that you know your basics, right? And I'm sure that if you take up programs at let's say for example USC, right? You will have all the opportunities to get that fundamentals, right? You will have all of the material resources and platform to get those fundamentals, right? So just learn those fundamentals, right? Nobody's expecting a fresh graduate to come and design, but at the same time, I think it's the aptitude to be able to think a little bit out of the box. As Professor touching, right? The need of the industry today is not for somebody to just come and just design, right? The need of the industry is to innovate and design, and the need of the industry is to challenge the design at the same time as well, because these are the people who basically, so you need to have that aptitude to question things, to challenge things. And in fundamentals, I won't go into technical, right? But basically, just get your basics right. I know academia out there now has become, much advanced, and academia overall is trying to basically, capture a lot of the industry needs as well. So that's actually very good. And as long as you get that fundamentals right, with the right set of knowledge and aptitude, I think that probably is the key to getting in. What skills basically, so touching on some of the fundamental, some of the technical skills, for VLSI industry at least, right? It's all about circuits, right? It's all about logic design, right? So try to get some of those well learned, and coding is essential part, right? Not necessarily coding at a level of a computer science student, but definitely coding is something that we do day in and day out. It is different formats, right? You need to learn any level of any basic coding, so that way at least one can test you on that skill of coding. I guess that should probably. Yeah.
Okay. Did you want to weigh in on this, Sandeep, or did he get everything?
Yeah. No, I think I agree with Vivraj. I would just underscore a few things that he said. One is basically the aspect of creative thinking, I think is important. Just to give you, again, I'm trying to give you this high-level example so you have a simple mental picture. Because of this coronavirus thing, so, places like USC are looking at their operations and to finding basically how they can save some money in the moments of this type of thing and changing their operations. So both from point of view of reducing money and also for point of view of how to keep things going. And in that process, you discover opportunities in that sort of moment of change and some scarcity. You discover things and people look at it and say, why did we do it that way? We should have always done it. There are certain things which we basically have realized that we should have never been doing that kind of a thing. We would have been doing this way. So basically what I'm saying is that when there is a moment of plenty, we do things in a certain way. When there's a moment of scarcity, because Moore's law is not giving you as much, you suddenly start to question, is that worth it? And that leads to basically a very creative thought process. And if that's not worth it, I don't want to waste that much resource on that little thing. And then you say, well, why was it there? You start asking the question, then you turn a dogma of 20 years. And that's one type of creativity. So one type of creativity is basically leads to a fundamental improvement and overturning of something that we've done in a particular way for 30, 40 years. And you start asking that question only for the first time because something drastically has changed, and usually a constraint. There is another way to think about creativity is an opportunity. We have never designed chips specifically for, autonomous vehicle. What does it mean? We have designed things that we have taken designs that we did for normal market, desktop computers, and we have put them into cars. When we did that, we had to do certain things. We had to make them rugged. We had to make them work at even a larger range of temperatures, so vibration. So we made them more physically robust, so to speak. But we didn't really change their design. But now the amount of computing that we require is so high that we have to build from scratch new computers specifically for cars, because the cars are not only doing some microprocessors to control their engines and emission system, but and their music systems and their car doors and windows, but they are also basically doing this cameras and LiDAR and so on, a lot of more processing. And so there's a creativity from opportunity. So there's a creativity from scarcity, and there is a creativity from new opportunity. And I think this is basically, something that you have to add to the domain of skills. So don't take your courses from the point of view of the professor is telling me these things, and so I should basically learn these things. But you should basically be thinking about, why is professor telling me this? Does he really, he claims that this is the best way to do this. Why is this the best way to do this? And I think I want students to basically get into that frame of mind. And that's really important, because we are reaching both creativity driving forces of scarcity, because the transistors are not getting faster, cheaper, and lower power, at the same rate and opportunity, because there are new applications that are emerging and that really require a huge amount of computing.
That sounds challenging and interesting, yeah. So Vivraj,
sorry, before we go, so I'm getting a few questions on the chat, so there will be a Q&A later, right? So I can answer those questions when we go to the Q&A.
sure, we can do that, yeah. So the other question is, students always, this goes towards preparedness. They would like to know, do certifications and online courses help when you're looking for a job?
Certifications and online courses definitely are a plus, right, on a resume. Anything more you get on your resume is good, because of course it has to be, I would think prevalent, it has to be related to the domain, right? Then it adds a lot more value. But I guess as long as you have your fundamentals from your undergraduate and the graduate program, right? I think that definitely, covers, I would say almost everything. And then any extra certification, let's say you get a certification in some kind of a code class, you get a certification in some kind of an industry related course, that's definitely a plus. I definitely see it as a plus. And if I have two resumes equivalent, right, and if there is a person with a relevant certification, that definitely can go a little long.
All right. So
and I'd like to add a bit.
Yes, I was actually going to come to you.
Yeah,
Candice.
I just wanted to add a bit there.
Yeah.
With my other hat, which is leading our continuing education area, I work with a number of our companies and organizations across the world to actually look at these type of certifications. And the big thing is, if you're going to look at, and we call them a non-degree type of program, a certification program, there needs to be a built-in knowledge assessment. There needs to be a way for you to let an employer know on your CV or your resume that you are at some way an expert or have been measured, your knowledge has been measured in that field. And that's where there's difficulty with a lot of what's available with massive open online courseware and some of the free information that's out there. It is wonderful, but in trying to put that on your CV or your resume, it's been really difficult for organizations to actually understand how much of that knowledge you actually know. And so with degree programs, they get that. And that is still an area with a lot of companies. It's in this gray area because they don't know if you're a master or if you are actually able to work in that field with a certification that didn't have maybe a built-in knowledge assessment. So find those type of programs where you can measure, get CEUs, of course, degree programs, but a knowledge assessment is something you should look for when you're evaluating those type of programs.
Okay, so I'm actually going to show some of the slides that you had, Candice, and maybe we can talk about, as I'm setting this up, do students need to have a citizenship or anything for any of these jobs, or can they be F1 students and people who have citizenships from other countries?
Absolutely. So I'll go quickly because I know that you have other questions. I want to make sure we have time for the Q&A. But we did pull a highlight of what the recruitment looked like last year for individuals who were finishing degrees with VLSI and embedded systems. So we had 96 organizations recruit our students in these programs last year with F1 student visas. So that's huge. I mean, these are companies that checked all the boxes and said that we are hiring, we are recruiting students, whether or not they're a US citizen. So that was not a concern for a number of organizations. You're looking for talent. And the talent is there. And so they didn't add those constraints. Now, of course, aerospace and defense, not a big recruiter in this area, but there are a number of other organizations. So this is just a snapshot of recruitment activities through the year. We have close to 4,500 postings that are available for our students. And this is just one academic year. Close to 200 unique organizations come and recruit our students at fairs. They come and present information sessions and host signature events and workshops with their teams. So all of these activities still take place in the time of COVID-19. Everything is virtual. But this just shows that there is a lot of connection that you would need to start to make when you begin a degree program and you're looking at those full-time or internship opportunities. And in the next slide, you can see what this looks like for this specific program area. So again, like I mentioned, 96 organizations recruited our F1 students in this field. There were 61 unique job postings that year. 38 of those companies physically came to the Career Expo, which is not the #1 way to recruit. It's the most visible way to recruit because it's a 2-day event when everyone sees the companies and sees the students. But recruiting and connecting, that's a whole year-long process. It usually happens in auditoriums, sessions that might not be in a quad, but still the type of event you should attend because that's where the connections are made. And 20 of the companies specifically hosted information sessions about opportunities within their organization. Now, those sessions are extremely important because you might think certain companies are hiring for people in your field, and you won't even realize that there are companies that were never on your radar that might be, having a huge investment. Maybe they're doing a complete shift in their business model, and they're hiring students with a VLSI background. So something to be mindful of. You will learn a lot in these sessions, and when you're on the USC campus, and other universities do this as well, if you're invited with a specific background, you're invited for a reason. That means an employer is looking for somebody with your skill set. So even if you don't make that connection as to why Hewlett Packard or someone might be reaching out to you because you haven't maybe heard of some of their recent projects, there's a reason why they're reaching out. And then the next slide is just a highlight of the companies this past year who were hiring students with this background at USC. And it's a few slides. I won't read the names, but some are just regular recruiters in the area: BAE Systems, Apple, Cisco, NXP, Semiconductors, NVIDIA. Some of them just always having a regular group of students that they're pulling from USC for internship and full-time opportunities.
I need to put Marvel up there. I don't see Marvel up there, so I'll try to.
Yes, that means last year we didn't have you. We always,
Okay.
yes, I love it.
I promise we'll work together to get that out there.
Perfect. Students will love that.
Very good. Yeah, there you go, Candice. You can get Marvel on the list. I'm sure they were on the list before.
Yes,
Yes.
you did recruit before. And this is a list of just some of the titles that students who graduate, they complete something called the First Destination Survey. And so this is an optional survey, but it at least lets us know where students in different backgrounds are going. What are they doing? What are their job titles? And so here's a list of just shared position titles that our graduates in May provided to us. So everything from design verification engineers, a number of SOC verification engineers, a good number of digital design, product design, senior engineers, and engineers. So you can see some similar job titles, but this is just a highlight of the roles that the students were being hired into upon graduation.
Fantastic. Okay.
And this is just the team. If you do choose USC, it's very unique that we have a career center dedicated to our School of Engineering, in addition to the USC Central Career Center. Not many universities have this. So this team is dedicated to working with the engineering students as part of our Engineering Career Center.
Yeah, and they're doing a fantastic job, as you can see from the very long list of companies that are hiring.
They're busy.
So, having a really active career center has been a huge asset for our students. So, and Candice is doing a fantastic job. So, Candice, I have one other question for you. Mm-hmm. When a student is looking for an internship, and they really may not have very much experience, how should they approach a company?
Well, they should still approach the company, but think with a different lens. So if you don't have that work experience yet, you need to translate what you've learned in the classroom or the lab into what you will contribute to that organization. So you do have experience, it just might not be traditional work experience. So what I would recommend is look at your academic projects a little differently. Maybe have a conversation with some of your past faculty members. And if you're not sure what that translation would look like, have a conversation with a faculty member and say, we worked on this final project. How do you see that translating to success in the workplace? That could be a talking point with an organization. Now, a key reminder for all students, anything you put on your CV is fair game for a conversation. So if you're going to list academic projects or research experiences, be ready to talk about them at length. Be ready to explain something as if you were working on that project for a year as part of an internship. If you don't feel comfortable speaking at length about an academic project or experience, don't put it on your CV. The reason why it would be there is to highlight what you could possibly do for that organization later on. So it's very common when you're starting out with a master's or even an undergraduate degree, you don't have that work experience yet. Bring in that classroom experience.
Yeah. Vivraj, can you add anything to that? And do you have any advice for students who are looking for internships or maybe freshers just looking for jobs? How should they approach?
So I'd like to a little bit, again, reiterate what Candace just said on the last point, right? If you're a fresh graduate or an intern coming for an interview, right? We do know you have no experience of working in this, right? Even if you probably, have projects that are much relevant, right? We kind of basically try to test you on the fundamentals and the fact that what you put on your resume, right? As compared to somebody who's like a 10 years experience who goes for an interview, right? Things are slightly different, because there the discussions are more towards, what work is going on, what do you think of, here it'll be more like, okay, testing on what's there on your CV. So if it's there on your CV, you better get that right. If you put it on a CV and you cannot answer it, and I'll be very honest, right? That happens a lot of times because students, when they try to build up their CV, right, they are trying to put everything on there, right? Even if they're like a VLSI student has seen a C code once in their life, right? They'll just write, languages known C and C++, right? And I would assume that that person knows C++. So if I'm a champion in C++, well, you're in a bad luck because I'm going to ask you a lot of questions in C++, right? So it's okay to have less items on your resume, right? But the right items is what is important. That's basically just what to say.
Yeah, no, that's wonderful advice. So I just wanted to talk about our MS in electrical engineering and VLSI design. This is a program that will prepare you for a career in this area. And like I think Sandeep mentioned earlier, and even Vivraj mentioned earlier, I don't think you need a lot of preparation previously. You need to have a bachelor's degree in maybe electrical engineering, and you can apply to this particular area. We are one of the very first universities that started a program in this particular area. Was this the program you went into, Vivraj?
Yes, absolutely.
Okay.
So I came from an Bachelor of Engineering from Electronics and Telecommunications, in fact, and and when I joined about more than a decade ago, right? Not many universities are offering, and in fact, when I had compared this program, by far USC had the most latest program, and I'm sure it's still the best across out there.
Yeah, it is. So if any of you are interested in this particular program, feel free to write to me. My email address is given over there. Also, our website is uscengineer.com, and that will take you to all the programs that we have at USC, and I encourage you to explore that. Before we go to the questions that we have in the chat session, I just wanted to tell you that the upcoming panel discussion on careers in game development is on 26th August, and we are sharing the previous recordings for all the other panel discussions that we've had in, say, biomedical engineering or computer security, financial engineering and machine learning and data science. They're already there on the same website. So now I am going to stop sharing my screen and go to the questions that you have. Vivraj, if you've seen a question that you'd like to answer, please go ahead and go ahead and start answering those questions.
Right. So before I jump into question, one point that I wanted to cover and that I did not get an opportunity is just to give a 1 minute brief of different domains inside VLSI, right? I don't know if we spoke about it, but maybe just to highlight, right? Within VLSI also, right, there are several domains, right? and one could be an expert at multiple domains. Like I have basically touched multiple of these domains, right? It starts from a basic architecture design, goes into RTL design, goes into a verification. Verification is becoming a very huge domain, right? Probably there are 2x amount of verification engineers in any team as compared to the actual RTL engineers, because the amount of testing, the amount of verification before that chip, I think the professor mentioned this, right? You don't want to send out a chip to the customer and find out the customer finds an issue with the chip, right? You want to test it in as many as possible scenarios as you can, right? Verification is a huge domain, right? Then after verification, it's like a process of, stages of a machine, right? And then there is physical design. Physical design is where you actually, translate that whole design onto the real, physical implementation point, which will actually get fabricated in the foundry, right? This is where is the marriage between the actual design and the technology, right? If this something goes wrong here, basically you've not translated your thought onto the chip correctly, right? So this is a very important step, and then comes the actual fabrication, which mostly happens in the foundry. This is where the technology is, and then comes back to the company, and basically that's where is the big domain of test and validation, right? You have to test that physical part in multiple scenarios, in scenarios which customers really going to use it, characterizing it, trying to also capture tons of data, how to make your next project better. So I think just to give a perspective, this VLSI itself is divided into multiple domains, and there is scope in every domain. As long as you have a fundamental, you can end up in any domain, right? So just wanted to give you that high level. So a couple of questions I have is, one question is, could you enlist the qualities an embedded systems engineer is expected to have in today's industrial world, right? Actually, before I take on that, I'll let Professor Sandeep answer that, right? If he has any data on that.
So, we had an interesting conversation some time ago. During every boom era, students come and say, hey, my friends tell me that a lot of the stuff that we are, covering is not that. Can you hear me?
Yes.
Yeah, we can hear you.
Okay, because something, I had to restart my WebEx, and again, something is happening. So, the question is basically really between, fundamentals and specific skills. And I did a survey of hiring managers at one point of time, small survey. I called 5 randomly selected hiring managers, got the names from students, and I called 6 or 7 of them. 5 of them actually talked to me. And one of the things that I realized is that engineering industry works sort of in a very fundamental way. Engineering industry doesn't expect students to come in on the first day and become independent contributors. They expect to basically train them on the practical aspects of the job. But they expect them to basically know the fundamentals. Even the parts of fundamentals that they think they will never use, they see value in that. So they know that there are certain types of, so we basically, for example, in our classes, we teach, when I teach VLSI design, I teach a lot about custom VLSI design. Most of my students, when they go to companies, they don't necessarily work on custom VLSI design. They work on a much more streamlined process where you essentially use standard methods and tools to basically do the design. And they get some training of that in some other courses also. But students say, why are you teaching this custom design if I'm not going to do it? Because I said, these are the fundamentals, and they will remain fixed for a long time.
Yeah.
And this is a knowledge that will be valuable to you when that one project, really challenging project that you manage to basically get on your plate and things don't work. Normal ways of doing things don't work. This is the element basically where your knowledge will basically be helpful. So I think with that thing, I always emphasize basically know the fundamentals, but you have to be nimble to learn the specifics quickly. And you have to be able to synthesize that. So it's that sort of understand the fundamentals, but be adaptive and comfortable with new things and mastering specific skills. And on top of that, I think have an element of asking questions. And that's the type of creativity that asking questions is really the way you can be creative in a workplace in a very respectful way and contribute in a big way. So I think of that as basically as the fundamental, focus on the fundamentals, be comfortable, develop enough, do enough specific things, and we make you do. We will teach you 2 different ways to do this, 3 different ways to do that, and we'll teach you, we'll expose you. But the ones you will use in a company may be a 4th one or a 5th one, and be willing to learn that. Don't think that this is the only thing I need to learn, and then I'll be fine. You just have to know that you have to learn new things constantly. And that's really the combined fundamentals with the ability and desire to learn things quickly and new things and ask questions.
Okay.
So,
Vivraj, you
so
want to add something to that?
Sure. So a couple of things, right? See, embedded systems to me, right? That question itself, right? It's very general, right? Embedded systems is a huge domain, right? There's hardware aspect to the embedded systems, there is system level aspect to the embedded systems, and then there is software aspect to the embedded systems, right? So you really have to kind of ask yourself which side do you really want to go, right? If it's good, we'll cover the hardware aspect in this topic, right? It's hardware basically starts again with the fundamentals of VLSI, right? You have to know your circuits and logic and transistors well if you want to become a good embedded systems hardware engineer, right? You want to develop the hardware of that embedded system, right? If you want to become one of those, who puts together a system and writes some of the compiler, you need to basically again then add some minimal elements of software coding skills or compiler coding skills onto your resume, right? So you got to learn that, So you got to have your fundamentals of hardware, but then again, as Professor said, right, you got to add those elements of maybe let me take an example, have some compiler coding skills, have some those kind of things, so that way you can actually build a system and write some software for it. So I guess that gives a general idea, right? So it's a very broad domain, right? And I feel I kind of see where this question is coming from, right? Is because people tend to think embedded system as the hardware, right? But again, VLSI is within the umbrella of embedded system, but it focuses more on the hardware aspect. So you got to understand what you are trying to do. I think one question that I have, and then I'll let you, right? I have one more question here. It says, how can wireless communications be applied in embedded systems, and what would be the challenges we are going to face? And I'll let Professor go first.
So, one of the things about embedded system is basically that it is a system that is designed for a particular application. And as such, it doesn't do only computing, and it doesn't start. I mean, so there's a way to basically think about cloud computing. And in cloud computing, basically everything starts off as a file and data, and output is data, and you do a lot of processing, okay? But embedded system is called embedded because it's embedded in the real world, okay? So the inputs are not necessarily data files. The inputs are coming from sensors. Inputs are coming from sensors that are far, far away. Things are connected to each other. So think about basically this idea of an entire aircraft fleet, carrier fleet, as an embedded system. You basically have all of these things that are networked to each other, and they are talking to each other. And the sensor that you're getting data from is on the plane, and you're on the ship. And so essentially, different sensors, communication modules are an integrated part of basically many embedded systems. Not every embedded system has them, but many embedded systems. Hopefully your hearing aid is not talking to anybody in Mars. But a lot of them basically have this component of computing, sensing, storage, networking, communication, and communication is just the foundational aspect of networking. So these systems are actually encompass, in my mind, in the best possible way, all aspects of electrical engineering. And they require basically, and you can come to basically, you say, I'm working embedded systems, and what do? I design sensors, It looks like you're a chemical engineer and electrical engineer first. You are basically not doing embedded system, but no, this person is actually contributing heavily. So it's, again, a very broad field, and it is basically not computing in isolation. We think about computing as files in, files out. Embedded system is not files in, files out, and it is really, that is basically what causes. So there are a lot of opportunities for this thing. So you hear about IoT, a lot of these things basically come and go as buzzwords do. As a buzzword, it may go away, but the idea behind that is a fundamental one, that there are highly interconnected systems, and they basically have assets and resources and information sources and things that they have to control everywhere distributed in the world, and or in a room or in a museum or in the supermarket, and you basically are, or a campus, and you're basically sort of building a system, custom system for that, and that's an embedded system. And so these are all important things that you have to think about. So it's a natural sensors, actuators, controllers, computers, communication devices, networking, all is integrated into embedded system. Not every embedded system will have all of these components, but the space of embedded system has to deal with all of them.
All right. That's a very thorough. We are getting to the end of our time, but we can take one more question perhaps, or perhaps maybe two. So let's get to this question. I had been meaning to ask it myself. How is quantum computing going to impact VLSI and embedded system sector?
So I think, quantum computing, so there are types of computing. So let me, if I take 2 minutes, I'm a professor, so I can't.
You have 1 minute, Sandeep.
I have to clear my throat before I start talking. One of the things that you have to basically, one of the things that seems to be clear, that whatever CMOS is not going away just because Moore's law stops. Moore's law is going to slow down. It's not going to stop right now for the next few a decade or so. But even when it basically comes to stop, CMOS is not going away. And the reason it's not going away is, unlike CMOS when it came after TTL or ECL, it essentially completely replaced, because it did everything that the previous computing technology did, but it did it better. So it completely replaced it. The juncture that we find ourselves in is we look at memristors, we look at spintronics devices, we look at quantum computing devices, at least in two broad flavors. One is superconducting, going back to the superconductive technology, which is I have a project on. I have a piece of a project on that one. And the other, what is more classically called quantum computing. Each one of these seem to be very suitable for specific tasks. So far, they don't seem to be promising as general purpose technology. So a quantum computing is basically not going to be carried in your pocket. Neither of the two types of quantum computing will be something that you can carry in your pocket for the near future, because they require very specific operation. They require the physics to be such, and they need to be in a controlled environment, just like computers. The regular computers used to be in these cold air-conditioned rooms in this thing. So because of that, and there are other limitations. The quantum computers, which are typically called quantum computers, are good for certain types of problems. They are not necessarily good for word processing. They're not good for refreshing your screen. And so there is basically going to be always this sort of so they will play a role. They will play a role in specific problems because they are very powerful for those problems. But they will basically be kind of a back office, or you can think about it as a cloud type of technology that will be used very heavily for some very heavy compute-intensive applications that are very specific types. A lot of other things will become heterogeneous, and so there'll be a sort of this world, and that is also very exciting. This end of Moore's law is very exciting, because now as a VLSI engineer, you not only need to know CMOS, but you need to know 6 other technologies. So, it's really the exciting part of this. The whole thing is that the frontier opens up. It doesn't close. It doesn't replace. You don't replace A by B. You add to A, B, C, D, and you have to basically understand that.
Wonderful. Vivraj, you want to pick one last question that we can answer?
Sure. I think one of the questions that's coming up is, please comment on the scope for digital versus analog versus mixed signal design engineering jobs. Let me start on that. So, to be fair, right? I think there are enough opportunities in all the domains, right? But definitely, it'll be unfair to say that digital by far is a bigger of all these, right? Because of the applications that we have seen, right? Digital, right? But at the same time, every digital component will always have some kind of analog or mixed signal component going there, right? So it's not that either analog or mixed signal is diminishing, right? There are opportunities. Digital by far probably has more opportunities, right? Digital design, meaning it could be, RTL, it could be verification, it could be anything, right? But at the same time, mixed signal opportunities are increasingly growing because of the amount of communication devices, right? See, every communication device will have a lot of mixed signal components in that. So there is a need, it has been there, and there is still a need for advancement in overall analog and mixed signal, right? And with technology, hitting a wall in terms of process, more and more avenues have to be found out for taking these analog designs to the next level, right? So I would say analog and mixed signal actually has by far more research opportunities to take it to the next level. Yeah, I mean, I still see equal amount of jobs out there, so I don't see any problem.
Okay. Candice, did you want to add something to that? Okay, so I know Candice gives a lot of good advice to people looking for jobs. You want to have some closing comments on that, Candice?
Yes, I honestly, looking for a position, whether it's an internship or a full-time position, is a part-time job for a student. So I mentioned that because if you wait until right before you need those opportunities, it could be too late. The opportunities are there, but it does take time, and you want to make sure that you're finding something that's a fit for you. So as soon as you begin a program, undergraduate or graduate, start having conversations with your faculty members. If you have a career center, meet with the career center, go to information sessions, learn about the opportunities, and just get yourself out there. You'll also find out which parts of your field you're attracted to. And so if there's a specific organization that's doing work in that area, you can align yourself with them. Instead of taking the first opportunity that's available, you can be a little bit more discerning. So just network, get out there, ask questions, be a sponge, and learn and realize that you are going to be competing against individuals who are taking the same exact classes as you. Your colleagues that are sitting next to you in class are also applying for the same positions. So how are you going to make yourself distinct? How are you going to stand out? So think about what you're gleaning from the classroom experiences. Think about what additional things you're doing and how you can explain that to an employer who, in essence, could be meeting with 20 people with the same academic structure that you have. Find out how you can make yourself stand out and those little extra things that you can do to glean more information from the classes that you're in. So that's just a quick piece of advice.
No, it's a great advice. Any last piece of advice, Sandeep, before we wind up for the day?
No, I think, one of the things that I say, this crowd is basically international and heterogeneous. So one of the things that I point to them is basically simply that, if you choose a profession, you're going to be in it for 40 years. Okay. What interests you is almost more important than where you think the opportunities lie. Because you're going to do this for a very long time. And so think about that and emphasize that a little bit. And if it is basically interests you, you should think about your not extrinsic reasons that, okay, there are more jobs here or whatever. It's a small component. But the way I look at it is that in electrical and computer engineering or computer science or almost any area of engineering today, there isn't a specialization you can pick in which you won't have opportunities if you're really passionate about it and you really train yourself. So I think it's not a difference between starvation and wealth. It is really just, differences. There are differences, yes, of opportunities, but really not for people who are really interested in the field. I think one of the important things you have to say is that even Vivraj said, all things being equal, these things may matter. Candice said, anything you put on the resume, you're willing to talk about it. If it excites you, if you are taking an online course because it fills your brain with knowledge and it gives you some understanding, that's a great reason to take an online course. If you're taking an online course because you can put it on your resume, I'm not for it. I do the same. So what I'm saying is that what interests you intrinsically, I find that interesting. I find looking at polygons interesting. I find these properties of polygons to be interesting. And you may not have a vocabulary to say this. A mathematician says this theorem is beautiful. You don't appreciate that, but you somehow are drawn to these polygons. Or you are basically this detective who really want to do this validation type of stuff and debugging. And this is a very complicated thing, and this is a very complicated system you're dealing with. So you have to have intrinsic interest, and you're doing things because you want to learn. You are doing things because you want to contribute.
Now
That's the mindset I would like you to get on, because I think there are opportunities in practically anything you do in electrical and computer engineering. There is no dearth of opportunity.
Good advice, Sandeep. I think that actually holds good for pretty much any field. But yeah. What about you, Vivraj? What's your closing comments and advice?
No, I think my closing comment is that, again, emphasize on what you want to do, right? Again, I see a lot of questions and comments coming related to the embedded systems, right? Do some research in, about which domain of embedded system you want to, you like, right? If it's hardware, then you have to start with VLSI, right? VLSI is the basics, right? So you have to basically start with VLSI. And don't think of the fact that if you end up taking a course in VLSI, a master's program in VLSI, right? You will end up in the VLSI domain. I mean, you will end up working on a chip, right? You still have opportunities to go and work on an embedded system platform, right? Like I have my, friends who graduated along with me. I'm doing a chip design, but they are now pretty much building embedded system platforms. I have a friend who works for a company called Waymo, and they pretty much do self-driving cars, So he graduated in VLSI, and he's working for that. So basically, there are opportunities are vast out there, But again, pick what interests you, because you're going to get stuck here for, Professor said 40 years. I would say rest of your life, So yeah, that's it.
Wonderful. Thank you to all the panelists. Thank you, Sandeep, Candice, Vivraj. You guys have been wonderful. And I think we've given the audience a lot of great information. So I appreciate you taking the time and being here today. Thank you to the audience for being here. We hope you enjoyed this and also found it very useful. So good luck with your careers. Stay safe.
Bye, everyone. Thank you.